Okay, so we're going to do some examples of Hilbert spaces. Okay, so I'm going to follow the book of Salsa. So Sandro Salsa's book. So this is chapter 6, and in particular the section is 6.3. Okay, so we are kind of skipping, like this is already page 358, right? But it doesn't mean that teach you a lot, because that it doesn't mean you have to the partial differential equations is not an only way to organize it. Okay, so it's not like calculus 1 that you had to do differentiation, then integration, and so on. So we're gonna set up the spaces. So it's gonna make sense. What are we gonna do? The calculations we're gonna do. Usually engineers don't really care about this part, but since we are mathematicians, we take care of this part. So let me say that our first example is, well, first I need to recall that with the inner product, right? Note, let's say a note. Using the inner product in the vectoral space, right? Of the vectoral space B, we can define a norm. So what is a norm? A norm is basically the generalization of the absolute value. Okay, it's a notion of distance. So you know absolute value. So what is absolute value? Absolute value, you have x, you have y. You want to know what is the distance between x and y. So the distance between x and y is x minus y, right? If you are, for example, in R2, okay, you have two vectors. This is x and this is y. Okay, so this is x, this is y. So you want to know the distance between these two guys. So the distance is the norm of x minus y. So this is, that vector is x minus y, and then that's the norm is the distance between those two vectors. Okay, so that's the generalization. So let's define norm. So we keep moving in these definitions. So this is from the book. This is Salso's book. This is section 6.2. So let's define the norm. So let definition norm. Okay, let me put, I like to put my definitions on green, so let's put it on green. So let X be a linear space or a vector space over the scalar field reals or complex. Okay, so the scalars can be real or complex, so you choose. A norm, and that's the definition, norm in X is a real function. Is usually you put this point to mean that you're gonna get an element of X and you're gonna assign a number. So for example here you got a vector and you assign a number, okay? But it can be abstract, okay? Such that for each lambda and every X and Y that belongs to X, the following properties hold. So that means property number one of norm. The norm of any element of the vector space is positive and is zero if and only if the vector is zero. Okay, so this is called positivity. Okay, so that means this is positivity. This is called positivity property. So it is distance, right? So think in norm like distance. Is the way we understand distance in mathematics. Okay, so the distance you want it to be positive, and the distance is going to be zero if and only if that's the vector zero. This could be vector. Property 2 of norm says that if you have excuse me, as a number times the vector, that gives you the absolute value of the scalar times the norm of the vector. Okay, so this is another property, and another property is the norm then X plus Y excuse me, is then a triangular inequality, is the sum of these two guys. So this is triangular inequality. So you might remember this one for the Pythagoras theorem, right? So you have in Pythagoras theorem you have X, you have Y, right? Well, in this case it's not exactly not exactly that, but yeah, I guess it's not a good example. So this is the what I want to say. Let's call it this A, let's call this B. This is A, this is B, and this was C. So this was C squared equals A squared plus B squared, right? So in this case it's different because we don't have equality, we have inequality, right? So yeah, and it's different because you have X, you have Y. So what is X plus Y? Is this guy. Okay, so what it's saying is that this guy, the norm of this guy, the distance of this guy is less or equal than the distance of this guy plus the distance of this guy. Okay, so it's called triangle inequality. But it's not really equality, so that's what it's called triangle inequality. Okay, not very, must be a better explanation than that, but anyway. So there is something else. So with this norm you can do all the calculus, okay? Because remember the absolute value, how important was absolute value. So here you take your X, there is your vector space, but your vector space with inner product could be matrices. Okay, we're gonna see that in a second. Matrices could be like linear algebra. All those vector spaces you saw in linear algebra, it's some of them can be defined a norm, or you can provide an unknown, but well, not for everybody, but for most of the examples that you saw in linear algebra, all of those spaces are gonna have a norm. Okay, and the last step, okay, and last step is a norm induces a distance. So this is a norm space, but you can define distance. So a norm induces a distance between two vectors. So as I said, the distance between two x and y, in this case you see like this guy, you see x and y, so it's gonna be the norm of the difference of x minus y, and that's gonna be a distance, okay? And so which makes x into a metric space. Okay, so look at what we have been doing. First, let's make a little story here. First, you have the real line, right? Then you learn about the complex numbers. Okay, and in both cases, what your notion of distance is absolute value. Okay, absolute value. Then you start making vectors. So this is R2. Okay, you have x, you have y, and then you define an inner product. Okay, and turns out that this inner product, if it can define a norm. Okay, so the inner product of okay, I haven't told you that part. So it turns out that for Hilbert spaces, or for vector spaces, with inner product, the inner product and take the square root of that is gonna give you, well, let's put it like this, it's gonna give you the norm of x. So in vector spaces you have inner product. Okay, so in R2, R3, R4, all you have is this inner product. Further, if you take the square root of this, you'll get a norm. So how do you define the norm? So you have you just take the square root, and even further, you can make a norm. So how do you make the norm? You take not a norm, a distance. Sorry. So you make a norm, then you have a metric. So metric is distance. So to do the distance of x and y, it's gonna be the norm of x minus y, where this guy is the inner product. So basically, what you are doing here is the inner product of x minus y square root. Okay. So we have been generalizing the concept of distance of the real numbers all the way to vectors, and we're gonna do more. We're gonna define it for functions and also for matrices, but our general objective is functions. Okay, so we want to know what is the distance between two functions. Is that weird? So let's say you have x squared and then you have let's say a square between minus 1 and 1. Okay, and then you have f of x equals x. Okay, so you can find the distance between x squared and x. Okay, weird, right? Because they are touching each other, but you can define a distance. Okay, uh, um, uh, in well, depends on what space you are. So if I want to compromise, well, because we are in minus 1 on 1, it's probably okay. Okay, but so yeah, well, the idea is to 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 get two functions and define the distance between two functions. Okay, and remember the beginning. Our initial idea was what is the distance between 2 points. So we just take the absolute value, right? So, but if you're in school, you just take a ruler, right? You take a ruler and measure here the distance, right? To look at how much we had been advancing. Okay, so that's why you need your mathematics to get a good idea, define it properly, and keep generating. So you can define a metric, and this is another definition. That's a metric space. So definition, metric space. So a metric space is a set M in down with a distance. So let me put here this page 353 of the book, okay? With a distance that takes two elements of the space and assign to a real number, satisfying the following question, satisfying the following three properties. So in your real analysis class, and you had to see this, okay? But here we just do the easy ones. Well, not the easy ones, the best ones, okay? The ones that are really useful, okay? The ones that we use in physics, okay? So first, property of distance. Distance of two numbers must be equals to 0, bigger or equal than 0, and the distance of two elements is 0 if and only if x equals y. Okay. Property 2 of distance. The distance of x to y is the same of distance of y to x, right? And property 3 of distance. Distance of x to c is less or equal than distance of x y plus distance of yc. So maybe this one is let's put it like this. So this is x, this is y, this is c. So distance of x to c is this one. So it's saying that the distance of x to y plus the distance of y to c is bigger than this distance. Okay, and it makes sense because why? What do you think it makes sense? Because there is a principle in geometry that says that the easier way to connect 2 points is a line. Okay, so that's what is called the triangle inequality. Okay, because the shorter path to connect 2 points is a linear line. So here you are not following the linear line. You are kind of following like a taxi, right? From here to here, you have to go this street, then turn left. Okay. Okay. So then we have a distance. So with distance, you start doing your analysis. So you say you took a topology class or a real analysis class. once you have distance, you make a ball. Sorry, my pen for a second. This battery happens in every video. So you choose a point, right? And then you make a ball. Let's say this point is x0. You make a ball around this point of distance d, or let's say distance 1. So that's a ball. Okay, but your distance can be not necessarily can be a ball, depending on the kind of distance you have defined. Your distance could be a rectangle. Your ball could be a rectangle. Okay, depends on what distance you define, or it could be like this figure. Okay, so distance is an abstract thing. So it depends what distance you choose, but for us we are just gonna use the ball. Okay, and it's beautiful because turns out that in Rn, as long as you are in Rn, this is finite dimensional vector spaces, all these distances are gonna be equivalent. Okay, so it's beautiful. But now we are doing partial differential equations, and this is really interesting. All the linear algebra you learn, okay, all the linear algebra is short because we're gonna work on functions. So your point in linear algebra was an element of a vector space, so something like that. Here our points are functions. Okay, so we work here with functions, not with points. So that's why this class is very interesting, because you're gonna see that you can do many things. You improve your understanding of mathematics, but then you apply it to real life. So I think it's a very beautiful topic. Okay, so far we have vector spaces, but we had learned basically that with a vector space, and if the vector space has an inner product, I can define a norm, and with a norm I can define a distance, and with a distance I define the topology. Okay, I know the name is scary, but that's what it is. It's just to find the topology, you just need to understand how do you measure distance, and basically you just wanna know how those balls looks like. Okay, so to finish this introduction of definitions, the last thing we need is the definition of a Cauchy sequence. Definition: Cauchy sequence. So in your calculus 2, you saw different examples of sequences, right? Examples of sequences. For example, 1 over n, right? So you learned that sequence was 1, 1/2, 1/3, 1/4, and so on. That's what is a sequence, right? So a collection of points, right? And this sequence was converging to 0, so it doesn't trespass it. So 1, 1/2, 1/4, 1/3, and they are going to 0. Never touch it. That's a sequence. Okay. So a Cauchy sequence is a very interesting sequence with the following property. So a sequence let's call it x sub m is a Cauchy sequence. Let's say this is a sequence of elements of x, right? Is a Cauchy sequence if the distance of any points, well, you take if this distance goes to 0 as m and k goes to infinity. So okay, so what does it mean in easy terms? This, it means that after a point, so these are your sequence, after a point, these guys, let's say after 1,000, they get really close. They're kind of starting to accumulate. So they are not spreading like this, okay? A Cauchy sequence, after, let's say, 1,000, 1,000,000, the sequence gets really close. So they get too close, so they get to 0. So it's like they're accumulating. They start accumulating around 1 point, okay? So they're not doing this. They're not dispersive, okay? They are just accumulating, okay? So that's what is a Cauchy sequence. And finally, why do I need this? Because definition, a metric space in which every Cauchy sequence converges is called complete. Okay, so if you are in a space, sorry, it's getting, where every Cauchy sequence converges, is called complete. And now we're going to define basically what is a Banach space. Okay, and also we're going to see that a Hilbert space, well, let's just say what is a Hilbert space definition. Let's put it green since it's the most important one. Let H be a vector space with inner product. We say that H is a Hilbert space if it is complete with respect to the norm of the inner product. So remember, the norm is the inner product of this guy, okay? So this is the norm induced by the inner product. This is really beautiful, because remember, you have been using inner product, and we related the inner product with the angle. Remember, we said this is the two vectors, and then this is theta. We renamed the norm of B, or we call it norm, right? So the norm of B with the norm of U, and the cosine between the angles. Now, it turns out that if you have a sequence of elements of this space, a and they are a Cauchy sequence, it has to be convergent. Okay, so the definition is, the definition is kind of weird, but let's see now some examples of Hilbert spaces. Now this is section 6.3 of the book. So example 1. So now the book is more abstract, no? So by all means, go and read the book as much as you can. But the book, the book is basically a PhD book. It's really between master and PhD, but more closer to PhD. Okay. So, but it really contains so much. Okay. So I knew I like this book because I know that whatever I wanna cover is here. So I just had to choose some sections of some chapter. Okay. But this is just linear algebra. Okay. This is linear algebra reinforced. So it's gonna, if you haven't taken linear algebra, so it's gonna help you to your linear algebra class. And if you already took it, well, this is gonna be easier for you, or even helpful. Okay. So example, Rn. Jeez, again, I really need to change my battery. I think it was new. Sorry, so I had to change the pen. Okay, so Rn is a Hilbert space with respect to the usual inner product. So let me make sure this is Rn, no? So that means the inner product between x and y, and x is, so let's put it like this, x is x1, x2, until xn, then y is y1, y2, until yn. So the inner product is the sum. Also, you can put it like this. That's what you learn in calculus 3, inner product. And you have j equals 1 to n, and then is xj times yj. That's notation, okay? The induced norm is the norm of this guy is, let's call it norm 1, is the square root of the inner product, and this is sum of j equals 1 to the n. Oh, the book has a typo here. X to the j square root. Okay, so that's the norm. Okay, so this book is weird because this book says several typos, and the same from the first edition. It's a little bit disappointed. I'm writing the typos that I find, so I will send him an email. Okay. So even better, and this might surprise you. More generally, if you choose a matrix, let's say this is a matrix Aij, ij equals 1 and to the n, it's a square matrix. So that means A is something like this, right? So A11, A12, 2, 2, 2, 2, A1n, and then 2, 2, 2, 2, n and 1, am2, 2, 2, 2, 2, ann. So this is the notation for that, okay? So you have a square matrix of order n. Symmetric and positive. Then you have the inner product between two matrices, because this is x and y. Oh no, this x and y are Rn, sorry. So you can use any matrix that is symmetric and positive. So, okay, let's do this. If you don't remember what is symmetric and positive, just put it on your Wikipedia. Okay? Then you have x inner product with a y. So remember, if a is a matrix times y, that's gonna give me another vector. Or the same thing, ax inner product y. And then this is basically sum of aij xi yj I equals 1 to n. Well, again, this guy is missing some notation. So j1 2. So it's really a double sum. So he has another typo here. Another typo. Has to be a double sum because you have I and j's. Okay? So this defines a scalar product in Rn. So here you go. So you have Rn. So let's put A. So you have Rn can be a Hilbert space with the normal norm of your calculus 3, but also you can choose any matrix and define a new inner product, or even part C. No, let's put this another example. Another example. What about you have complex vectors? So it means the vectors can be like of the form I1 plus I. Okay? For this will be belongs to complex 2. Okay? So you have complex vectors. Cn is a Hilbert space with respect to the inner product so you get multiplication of the two guys here, and then the sum is gonna be xj yj conjugate. Then you have x equals x1 x to the n, and then y, so this is one vector, this is another vector, y1 yn. So basically, if you have complex vectors, as I said, one complex vector could be 1, 5, and 3 plus I. Okay, so you had to multiply times the conjugate. I already find the conjugate in one of the examples, on one of my previous videos. Okay, finally, why we were doing all this, guys? Why we were doing all this? Because we want to introduce L2, the Hilbert space. Okay, so example from the book. So you can choose. So let omega be an interval. So you can say AB. Okay. So L2 omega It's gonna be all the functions such that the integral of f squared between a and b, say dx, is less than infinity. Okay, so that basically all the square integrable functions. Okay, and you have worked with this space before, because in statistics that's what we do, right? So we want to find the probability of something, and we take the integral, right, to make sure the integral of the graph is 1, for example, in probability, right? So this is a Hilbert space. And he wrote, I'm gonna copy what he wrote in the book. Perhaps the most important one, even most important one, the classical ones, because you do quantum mechanics in this space. Okay, so you do classical mechanics in R3, R4, or whatever R you need, R3, R2, R1. Okay, quantum mechanics you need to do in this space. Okay, it's a Hilbert space with respect to the inner product. You get inner product of u and b in L2. It's gonna be the integral of u times b in the interval. Okay, let me see how much time I have. 42 minutes. Yeah, that's more than enough. Okay, so with this I have finished my review of linear algebra, complex numbers, and I have introduced you to Hilbert spaces. Okay, so, and this is chapter 6 from the book. So we will do more of this chapter in my next video. We're going to do basis, and then you're going to understand why do we need Hilbert space, and why this is the new mathematics. Okay, this mathematical physics, this is connected to mathematical physics, and that's why Russians on the 60s they were winning. They had more developed, the science were more developed, because they have all these Hilbert spaces. They use them very well with series. Okay, so those calculus 2 series that you saw, so remember, in your calculus 2 you saw series, right? So like, for example, sum of 1 over n squared, n equals 1 to infinity. This is less than infinity. This is convergent. So we're gonna do series, yes, but our series are gonna be with functions, sines and cosine series, and they're gonna be convergent. And then you're gonna like it, because we're gonna prove a lot of stuff and using good calculus too, a good analysis. Okay, but not all the way to the PhD level, but something enough, because I commented before that I like to use this analogy of the master degree. So in the master degree, you don't have to be Catholic to understand this, but it's like the purgatory. Okay, so Catholics, and I'm Catholic, so I can make fun of that. So Catholics believe that you can, once you die, you go to heaven once you spend some time in purgatory. So this is purgatory. So you guys have to review all your math, all your algebra, all your analysis, all your calculus, put it together, your differential equation. We are putting together with applications, and we're gonna see what is this good for. So when you go to heaven, you had a good intuition. You say in this purgatory you learn what you like. what you don't like, and maybe hopefully you like to do a PhD or go to work in a company, uh, whatever, or you wanna go to teach to students, so you'll have a better idea of what other things you could teach connected to what we have been learning. Hopefully to connect to apply mathematics and apply to computational skills, and because all this later is going to be computational. Okay, so everything is getting together. Okay, so but I will make a video every week. I will gonna make a video of reviewing what we did last week and what we're doing this week. So, and right now I'm not certain how much I'm gonna be able to do for this week. So this is my video for one day. So I'm working on my other video for the second day. So I will do my review of the week for when once I finish that video. So I tell you what I had done and what is gonna be for homework and when. Okay.